Okay, today we're going to continue with the limits. What I'd like to do first before we do that is to show you some of the things that I've added to the website. If you go into the link on unsolved problems, there's a link of 7 problems, which are the Clay Millennial problems, each of which will get you $1 million if you solve it, which is kind of nice motivation there. Now these are, I should point out, major unsolved problems in mathematics.
I think of it as a parent. If it's worth that much money, then I'm not even going to bother with it, because it means it's pretty hard.
Yeah, these are definitely not easy problems. For example, the Riemann hypothesis is one of those. The Poincaré conjecture, the Navier-Stokes equations, etc. So the very interesting thing about this, let's just click on the Riemann hypothesis. There's a series of lectures that were given at UT. So if you click on the link that's listed RAM, that's Real Player, it'll pop up a Real Player box, and if you have the bandwidth, it will download a very nice, usually between 50 and 70-minute lecture by the speaker. There's also an official problem description, so if you want the authoritative problem statement for the Riemann hypothesis, you click that and it'll give you the PDF file. So for example, this is the statement of the Riemann hypothesis. So you have a function called the Riemann zeta function, which is a function of a complex variable, summation n equals 1 to infinity. Let's blow that up a little bit more right here. So it's a geometric series in the complex plane, and they want to know for what values is it defined. And you can formulate that and relate it to the distribution of primes. So this is a very famous unsolved is your choice if you solve it. Okay, so the Real Player, I guess, here it is. So this is an example of equality. So I guess I'm taping a tape here, so it's going to go kind of slowly. Another link that I have is under the unsolved problems. There's a list of problems in here. There's some open problems in geometry. The hard problems, there's a link to the Fermat big theorem, last theorem. Also, there's an example of an NP nomial problem, which is the classic game of Minesweeper. So if you click that link, you'll see why the Minesweeper game is basically an NP hard problem. Now, what I'd like to do today is finish lecture 6 on limits. So just to summarize, we saw how limits could be used in geometric terms by Archimedes' construction of the area of a circle. You can also trisect an angle by a sequence of bisections. So how does that work? Well, if you have a triangle, or an angle, I should say, so let's just draw an arbitrary angle here. Now, if you want to trisect it, that's hard, but if you successively bisect the angle and bisect it again into an angle, so this would be an approximation. This is theta over 4. This is theta over 2, and this is your angle theta. You can write the series 1/3. This is equal to 1/4 plus 1/12. That's a fact. It's 3/12 plus a 12 plus 4/12, which is 1/3. Which you can write as 1/4 plus 1/4 times 1/3. If you just substitute 1/3 in there, 1/3 is 1/4 plus 1/4 times 1/3, etc. And you get a geometric series, 1/4 plus 1/4 squared plus 1/4 cubed, etc. And this is, after all, a geometric series which sums to 1 over 1 minus 1/4 minus 1, which is correct. 1 minus 1/4 is 3/4, 1 over that is 4/3, 4/3 minus 1 is 1/3. So if you take 3 over 4 and then take this angle and repeatedly bisect this twice, so here and then here, add that portion of it, so you can come into the limit of a third over 3. So successive bisections would lead to a trisection of the angle, and this was realized and was an approximation for a trisection of an angle. Now, we talked about last time the Cantor set. The Cantor set, okay, I apologize for network problems here. The Cantor set, as we all know, is the set that you get by taking a unit interval, subtracting out its middle third, taking out the open interval 1/3. Each interval that remains, you successively take out 1/3. Now, what remains is, of course, an infinite number of real numbers, and it's called Cantor's dust. Now, note that when you take away a third, and then 2 1/9, and then 4 the 1/27, you're taking away a set of measure 1, and what remains is obviously a set of measure 0. Now, the Cantor set has a lot of really unusual properties. Now, one of the things you can see is if you write this in terms of base 3, what you're doing, here's 1/3, 1/3 in base 3, 1/3 in base 2. What you're doing is in base 3, you're removing everything with a 1 in its decimal or ternary expansion. So base 3 is ternary. So if you take all the decimal numbers between 0 and 1 and subtract out the ones with a 1 in them, you basically take out a lot of them, but what's left is quite a bit. Now, you can show the following. We'll continue to go down here. This is a function that's built on a Cantor set. So, okay, so it's 1/2 on the middle, it's 1/4 on this set, 1/8 on the set remains. So you can show that this stair-step function is continuous. Now, this is what I find really curious, and of course this is all well known, that every interval you remove is open, and there's a countable number, a denumerable number of open intervals, which is union is also open. So if you take this open interval from the closed interval, what's left is closed. It's the complement of this open interval, it's closed. So therefore it contains all its limit points, all its accumulation points. Now the Cantor set's a little bit different since the accumulation points are not isolated. Every point is an accumulation point. However, it's not dense because the Cantor set is nowhere dense, because every point in the Cantor set, if you surround it with an open interval, contains an interval inside that is not inside the set. So it's nowhere dense. However, every point is an accumulation point, and if that's not odd enough, it has a fractional dimension. Now we'll go show you in a second why it has Hausdorff dimension equal to 0.63 and what in fact Hausdorff dimension is. That'll be the subject of today's lecture. Okay, so that's a little bit about the Cantor set. We went through some of the links on fractals and chaos. I'd like to mention the one thing that we didn't really talk about last time was, and there's a link on it, the idea of Hausdorff dimension. So what I'd like to do is indicate how you use the limit process to discover extensions of the idea of a fractional dimension. So first of all, what could one possibly mean by fractional dimension? And it turns out that you cannot get this without the concept of a limit. Now, the concept due, and this is what's called Hausdorff-Vasikovich. Obviously named after these two guys. So it's a measure of the size of a set. So the rough idea of this is the following. You take a set E, and you cover it by balls of varying sizes. Okay, so just cover it with a set of balls. So the set E is therefore contained in the union of most likely a large number, it'll be a finite in this case, and since it's finite. So it'll be a set of balls of different radiuses. There could be a different radius for each ball, each centered on a particular point, and I just won't worry about that. So obviously, since this set is contained in this, the volume, if you will, I'll use that instead of measure, but the volume of E would then certainly be less than the summation of the volumes of all of these balls.
That's probably good now.
Right. It just has to do with the additive nature of the, you know what the volume of a ball is in whatever dimension you're measuring it in. And for a plane, it's pi r squared, so it's pi r cubed for 3 dimensions, etc. So you know an n-dimensional ball, and this just has to do with a property of open sets and how you define the measures on them, the volumes. Okay, so this is true. Now, it's obviously also true that as you make these balls smaller, the overlap region will diminish and you get a better approximation. This is strictly an upper bound. So what you should do is take all of these balls less than some epsilon and sum all of these balls of radius less than epsilon okay, and then what we want to do is take the minimum value of this and the limit as epsilon goes to 0. So we have to take the smallest value of this set. So we want to get the best area approximation or volume approximation. So for a given epsilon, we look at the best covering for the balls less than this epsilon, and then we look at the limit as epsilon goes to 0 of this guy. And what this is the Hausdorff dimension of that set E. Now, notice I didn't tell you what the dimension of the balls was. For example, it is possible that I could cover a 2-dimensional set with spheres. Right? I could cover it with a whole sequence of spheres. And what would that do to the dimension? Well, it turns out that the dimension of this 2-dimensional surface covering by 3-dimensional spheres, this limit will go to 0. So if you try to cover a lower dimensional object by higher dimensional balls, the Hausdorff measure of it is going to be 0. If you try to cover, say, a 3-dimensional object by slices, and then covering it by circles inside each of the slices, obviously it's going to take up an infinite number. You won't be able to cover it. So if you cover an object by balls which are lower dimensional, it'll be 0, or infinity. If you cover it by higher dimensional balls, it'll be infinity. And just like Goldilocks and the 3 Bears, if it's just right, you'll get a finite number. Now, unfortunately, and that's where this D comes in. D is the dimension. So if D is the dimension is bigger than the dimension of this object, you'll get 0. If it's smaller, you'll get infinity. So the question is what is the right value for D? Well, this is where Kolmogorov, who is another very famous mathematician in Russia in the 50s, defined what's called the capacity of a set. Now, what does that mean? That means if I drew a set here, and I cover it with balls of constant, so I set the ball radius to be epsilon, I cover this with the fewest number of balls of radius epsilon. And I count up the number. So N of E is the minimum number of balls of radius epsilon. Now, notice one thing. For example, if I took any line curve in the plane of length L, obviously you could cover it end to end with L over epsilon would be the number of balls, roughly. There's a little bit of overlap, but if it exactly measures out right, if it's an integer number of epsilons, then this is true. But the important point is that the number is proportional to epsilon to the minus 1. Now suppose you have any object in R2. This is R1. This is in the plane. I can cover it by balls of radius epsilon, and roughly it's going to take the area divided by epsilon squared, forgetting about the pi. So this is roughly the number. So n is roughly like epsilon to the minus 2. So clearly the number scales as epsilon to the minus power, where the power is the dimension of the object. And that's exactly what we define it as. If the number of covering balls scales like epsilon to the minus d, d is the dimension. Now, if I take the logarithm of both sides, this would say that the natural log of n would be like minus d times the natural log of e, or we'll write this as d natural log of 1 over epsilon. So in fact, I'm going to define my d as the ratio of the number of balls of radius epsilon divided by the log of 1 over epsilon, and then the limit as epsilon goes to 0. So clearly, this is infinity, but the ratio has to go to some number, and that number is d. Now, let me show you why the Cantor set has fractional dimension. Okay, so back to the Cantor set. Remember, we took the unit interval 0, 1, then we had 0 to 1/3, 1/3 to 1, and then this was divided into 4 pieces, etc. So this has 1 ball of radius 1. This has 2 balls of radius 1/3. We'll cover this set. 4 balls of radius 1/9. We'll cover that. So in general, at step p, after p times, I will have 2 to the p balls of 1 over 3 to the p radius. So this is my n, and that is my epsilon. Okay, so what is this limit? This is the ratio of the natural log of the number divided by natural log of 1 over epsilon, as epsilon goes to 0. So what is the limit of this? The log n is p log 2. And what is 1 over e? If epsilon is this, 1 over e is 3 to the p. So natural log is p natural log 3. And n is 2. So this is p log 2. The p's cancel, and you actually see that the dimension will be log 2 over log 3. And that's equal to 0.6 6 something I've forgotten. In fact, if you look at this, if I go back to the Cantor set, okay, down near the bottom, it computes that actually to a bunch of places. And here it is. The Hausdorff dimension of the Cantor set is 0.630929753, exactly. Now, just to show you another very nice definition of a limit, let me show you the Koch snowflake. This is a fractal, it's in R2. What you do is you take well, let's do it on a line, actually. It lives in R2. If you take a triangle, and then you take this and you take a triangle and put it on each line segment, would be another equilateral triangle, etc. So the limit gets you something with, really, gets kind of, what the heck is that as a limit? Okay, let's just do it in one dimension. I'll show you what okay, so let me just concentrate on one line segment. Now, let me take, this is in R2, and this I'll start off with unit interval 0 to 1. Then I'm going to put a triangle on here. And then on each triangle, I'm going to put an equilateral triangle, etc. So it looks like this first, and then this, and then this, and etc. So you can see, obviously, that this is one segment of length 1. This is 1, 2, 3, 4 segments of length what? 1/3, because it divides the interval into 3. This is 16 segments of 1/9. And if you do it p times, it's 4 to the p segments of length 1/3 to the p. So this is my n, and that's my epsilon. So again, 1/epsilon is 3 to the p. So log n over log 1/epsilon. Log n is p log 4. And log 1/epsilon is p log 3. So in this case, log 4 over log 3 is 1.2 something or other. But it's bigger than 1. So the Cantor set had dimension less than 1. It's clear, obviously, that you can't get a set that's contained in the plane that has bigger dimension than the plane. That would be impossible. Right? So, but you can have a curve made up of line segments that in the plane has dimension bigger than 1, which would be like a circle that has dimension 1. The Koch snowflake has about 25% more dimension, okay, if you can think of it that way. Okay, so we talked a bit about Hausdorff dimensions, and the dynamical systems has a lot of lecture notes in here from this link. The point is on that is that any system that you integrate, if it's autonomous, meaning that it doesn't depend on X, a simple integration scheme, Euler's method, will give you something like this, which is a function of yn with the parameter h. And this is an iterative or recursive iterative function. And the question is, does yn go to a limit? Clearly, by our previous discussions, there are conditions on h when this will converge or not. And for a particular system called the logistic equation, which looks like dy dx is just a quadratic, ax, say 1 minus x. If you look at this, excuse me, that should be a times y, 1 minus y. This would be yn plus 1, would be yn plus a, h, yn, 1 minus yn. If you look at this and iterate it, depending on the value of the parameter, you can get a singular limit point, 2 oscillating limit points, up to n, or just chaotic behavior. And that was on the link, the logistic link on the fractals. Okay. Now what I'd like to do is go to the remaining topics that I wanted to cover today on limits. So the first thing I want to do is talk about sequences. And just to motivate that, this is a nice little link here, and I'll then do some by hand. A sequence, the notion of an idea of a limit of a sequence is very, very intuitive, because if you just take a series of data measurements, you want to know what it is in the limit. And they actually motivate the sequence by means of this iterated function. So if you iterate cosine, it'll converge to this number. So cosine of the cosine of the cosine will give you a number that's between 0.7 and 0.75. But if you do that to sine, it converges to 0, all very, very slowly. If you did it on this logistic equation, well, who knows? It's all over the map, literally. So the question is when does a sequence approach a number? So the question is if you have a sequence, that means just a set of numbers, x1, x2, x3, etc., that are generated by some rule. When does the limit of this sequence, as n gets very large, make sense? Well, we talked a little bit about the epsilon delta for a function, but this is not a continuous function. This is a discrete sequence. So clearly what we want is this picture. If we have L, these points can be all over the map, but eventually they'll have to settle down to some number L. So the idea is, if you look at the distance, of course, between any point big enough, so if n is big enough, bigger than some number n, that this is smaller than your given tolerance. So all the values bigger than some index are within this window epsilon of L. So the idea is that given any small number, you pick it, there is a n, which normally would depend on the size of epsilon, so that if n is bigger than this amount, that distance is less than epsilon. That means beyond this point, n, everything stays within epsilon of the limit. So this clearly is the discrete analog. Now the question is, what is the limit? So for example, if I gave you a sequence, say, n squared minus 1 over n minus 1, or let's make that n squared plus 1, and then let's make the limit as n goes to infinity. What would be that number? Well, here is sort of the paradox of the definition of limit. If I knew what the limit is, I can verify that it is the limit by plugging it into the definition of the limit. But this definition of a limit doesn't tell me what that limit is. Now, of course, I could, if I just look at this, and suppose I'm smart enough to rewrite this as 1 minus 1 over n squared over 1 plus 1 over n squared as n goes to infinity, it's pretty clear what that is, right? This goes to 0, this goes to 0, 1 minus 0, but 1 plus 0 is 1. So you could actually prove, once you have this number, that this statement is true. But the $64 question is, how do I find the limit? Okay. So this paradox, if you will, of the definition being non-constructive is what led to other ways of verifying whether a limit could exist. So the idea of Cauchy sequences, etc. So that's what I have next in the link. A Cauchy sequence was, well, here it is. It just states that one of the problems with deciding if a sequence is convergent is that you need to have a limit before you can test the function. Okay, so Bolzano, or the Bolzano of our testing, was the first to spot a way around this sort of conundrum using an idea of Cauchy. So they say there's a Cauchy sequence if the terms of the sequence all become close to one another. So given any epsilon positive, you can find an n so that after that point, they all remain uniformly close. Now, a Cauchy sequence with a limit says that all the terms in the sequence remain uniformly close no matter which two terms I pick. What about this? What if I just said two successive terms were less than epsilon? Would that guarantee a limit of a sequence? This is not good enough. It's clear because you can provide a counterexample. Okay? One of the counterexamples that you can provide is the logarithm, for example. That's one example. And it actually comes from a partial sum of 1 over n. So x to the n, like logarithm. If you look at the successive differences of log n plus 1 minus log n, this is log of n plus 1 divided by n, which is log of 1 plus 1 over n. That number actually goes to 0. So it has to be less than epsilon as this goes to 0, but does log of n sequence converge? What does log of n converge to as n goes to infinity? It's obviously infinity. Right? You take a log of 10, it's 2, log of 100, it's 3, log of 1,000, it's 3, log of 10,000 is 4. So you can make the logarithms arbitrarily big. So successive differences is not good enough. You must have arbitrary differences uniformly close. Okay. Again, this does not require that you know the limit to show convergence. This will imply convergence even if you don't know L is not known. So that's at least one step better. Okay, but it involves the limit in a very critical way. Summability. That's a very important topic that people back in the 1800s, 1700s were really, really interested in, particularly after a guy named Fourier. So Fourier came up with the idea of these Fourier series, so C sub n times sine nx, and you sum from, say, 0 to infinity with some values of Cn which are known. And the question is when does this series converge? For what values of x? Well, clearly, if you put in x equals 0, it'll converge, but will this converge for non-trivial values of x? And this generally led to that when does a series of numbers converge? Well, this actually turns out to be a question about a convergence of a sequence, right? Because I could define, as you know, the nth partial sum, which is just the first n terms. And this series will converge if and only if the limit of the nth partial sum exists. Okay. Now, we've reduced it to the limit of these series. Now, there is an example of a function which is before the Weierstrass function. Let me just go through that. The Weierstrass function is an example of a Fourier series. It's given by putting the CNs to be a geometric series and then taking sines of, I believe it's 4 to the power n x. And then saying, okay, I'm going to sum an infinite number of these, maybe 0. And what is this does this function f? So I put in a value of x and sum the series. If the series sums, then that's the value of f. Now, it turns out this actually is an absolutely convergent series, right? Because if I write this as an a sub n, the summation of the absolute values of this is less than summation of 3 to the 4th to the nth power from 0 to infinity, which is just the geometric series 1 over 1 minus 3/4. So since this series converges absolutely, I get a uniformly continuous function here. So this function is nice and continuous, or at least exists for every x, and you can show that it's continuous. So this exists for every x. And it's in fact not only does it exist, it's nice and continuous. Now, so I have to put a new, what is the derivative if it exists? Well, if you differentiate that series, well, you still get the 3/4 to the n, but if you differentiate the sine, you get a cosine, and you pull out a factor 4 to the n, which conveniently cancels with that, and you get n equals 0, 3 to the n, cosine 4n x. Now, unfortunately, this guy diverges for every value of x. This is a bad series. Okay? So this, because of this term 3 to the n is just growing too fast. So this diverges for all values of x, which basically means the derivative doesn't exist. So you have what? You have a continuous function, uniformly convergent series, exists for all x, and is continuous, and yet its derivative exists nowhere. Where is that? I just wrote it down. Okay, so its derivative does not exist for any x. Now you can actually see a picture of this. You can imagine it's probably not very smooth, right? A continuous function that's nowhere differentiable, here's what it looks like. So here's a picture of the Weierstrass function. You can actually, in this case, rub a band around the function here and zoom in, and you can see that guy's pretty rough. It oscillates around. Well, there are even worse functions around here. This Cantor function, which you get by removing the middle thirds and then graphing it. That Cantor function, actually it was not this link, at the previous, on the Cantor, there was a picture of the Cantor function. Oops, maybe it was there. Ah, here it is, Cantor function. No. So here's a picture of the Cantor function. They just set the value on the interval that they take out equal to the left endpoint of that interval. So essentially, you can show that this function is actually continuous. That's pretty clear. In fact, it's differentiable almost everywhere, but its derivative is equal to 0 almost everywhere. So this is a continuous, monotonely increasing function which is differentiable everywhere, and its derivative is equal to 0 almost everywhere. So that's certainly one of those pathological kinds of functions. Okay. In mathematics, counterexamples are almost worth their weight in gold because if they're non-intuitive counterexamples, they generally lead to tremendous insight into exactly what is necessary for a theorem to be true or not. If you can just tweak the hypothesis just a little bit or find a counterexample, that gives you a huge insight into the role of the assumptions in the problem. Now, another limit is, of course, integration. Everyone knows integration. So integration is a natural place for limits, and I'll show you in a little bit. But if you take any function, you know just from the definition of the Riemann sums that you can approximate the integral, say by a lower bound as the inscribed rectangles, or if I were to do midpoints or otherwise. In this case, if this had an area, I could trap it between the upper sums and the lower sums. So if this area, which I'm going to call this integral from A to B, I could trap it between an upper sum and a lower sum. And obviously, if the lower sum goes to a number and the upper sum goes to a number, then what's the integral? It has to be I, right? So you can actually indirectly compute the integral by just showing that the sequence of lower sums, which is increasing in this case, and the upper sums, which is decreasing, go to the same number. Now, if the lower sums and the upper sums do not agree in the limit, what happens? You've got a function which is not integrable. So, for example, if you have f of x was equal to 1 if x is rational, and 0 if x is irrational, Right, exactly. If I graph that, there's enough points up here. On any interval, I have to include 1, so the upper sums are all 1, and the lower sums are all 0 for any partition that I have. On any interval, there's always a rational number, so the maximum is 1, and the minimum is 0. So the lower sums is identically equal to 0, and the upper will be a constant, which say 1. So these never converge. You get a sequence of zeros and a sequence of 1s. So this function is just not integrable in Riemann sense. Now it is integrable in other senses, but you have to extend the idea of what obviously integration is. Okay, you have to have Lebesgue integration or other types of integration here. Okay, so that's an idea of a limit. I happen to have an applet that I wrote for a project, calculus on a web project. And here it is. Actually, you can toggle them. Here's a good value. Now you can actually change these, like to right endpoints or midpoints, or you can increase them to say 100 and get a better approximation. So it's pretty clear from this that the finer you make the divisions, the more closely you can approximate the integral. And that does make sense. You would define, in this case, the integral, if it exists, between a and b of f of x dx would be the limit of some appropriately chosen points and appropriately chosen intervals, again, say from 1 to n, as n goes to infinity. If this limit exists, and if you can appropriately define these points at the midpoint, etc. So you could define an integral indirectly by means of a limit. This has got to be one of the mathematician's favorite tools, is explain what you know by a limit. Now, another example of a limit that I want to go through is a delta function. Some of you certainly have heard of a delta function. Now, I'll more or less do the engineering definition rather than the distribution theory that mathematicians have. But the intuitive idea is the following. If I have a function, say that's 1, say on the interval, then I extend it to be, say 2, height 2 on the half interval, and in general, over an interval 0 to 1 over n, and make this guy n tall, obviously the area is equal to what? 1. So the area is equal to 1. Now if I call this f sub 1, f sub 2, f sub n, the question is, does f sub n converge to f in any sense? Not just the value of x, but what does this mean? What is the limit as n goes to infinity of f of n of x? Well, obviously this would have to converge to a function which is 0 almost everywhere, right? If this limit did exist point-wise, then it's clear that the only non-zero value you could have would be at the origin. Because after a while, any point that's bigger than 0, you shrink it, and eventually everything beyond a certain n is going to be 0 there. So it's clear that if the limit existed, it would have to be f of x would be equal to 0 if x was not 0. And who knows what it would be if x equals 0. What happens there? Now, the reason why this limit can't exist in this sense is if you look at the integrals. If you look at integrating...
The integral of the limit is not equal to the limit of the x.
Right. If you take a function f of x here and integrate it against this, or I should say g, that's my function g, and this is my f sub n right here, 0, 1 over n. The integral from, say, minus 1 to 1 of any function g, capital F n of x, dx, what is that? Well, it's approximately the value of g somewhere in this interval times the area of f, which is 1. So this is like g of x star for some x star in that interval, right? 0, 1 over n. So it's clear what's going to happen is, as n goes to infinity, the limit has to have this property, that if I integrate it against g, it picks out the value g0. And this is exactly what we mean mathematically by a delta function. A delta function does not exist in the classical sense of a point-wise defined function. It can't, right? Because if I had a function which was 0 everywhere but at a point, and I integrate it against a continuous function, what do I get? Well, if I multiply g by a function which is 0 everywhere but at a point, I get a function which is 0 everywhere at a point, and if I integrate that in the Riemann sense, I get 0, not g of 0. So this has to be a function that's defined in a more complicated way than just a pointwise. But again, this idea of taking a sequence of functions and looking at a process as n goes to infinity gives you something new. Limits are used by mathematicians to explore into places that previously were unknown.
Now,
So,
if then the approach F uniformly, then the limit of the integral would approach the integral.
right, and this says that it can't be uniformly because the uniform convergence of a series of continuous functions would be a continuous function, and you can't have a continuous function at zero only at a point. I mean, non-zero only at a point. So this cannot be uniform convergence, certainly. So these are the kinds of things you can have the following kinds of questions, and in fact, let's look at some different types. And this will be your homework number 4. So I'm only going to give you some representative types. You're going to be given a specific set of problems, not what I'm going to write down now. But there are function limits, and these are generally of the form, the limit of f of x as x approaches some number equals what? Calculate the limit. You can have graphical limits. You could have some complicated graph, and then, where is the limit at some point. You could have sequences. What is the limit of x sub n as n goes to infinity? You could have the limit of functions, like what is the limit of fn of x as n goes to infinity? Is that a function, and if so, what properties are preserved under various types of convergence? So again, this is another function sequence.
I don't understand the difference between a function and a graph.
Well, this is approach not to a point.
Sorry, the top two.
These two?
Yeah.
Well, this is just given as an algebraic. Obviously, this has a graph, and you can put it a point. So you could express this as this type of problem, but you may be given a graphical limit. Like I could, for example, give you.
What you're saying, how do you give the type of the problem?
Yeah, it's how it's phrased.
Okay.
Now, you could ask questions about function sequences. You could also ask questions about limit in what sense. So, for example, do you mean that fnx minus fn, f of x, the limit, that the maximum over all values on this interval goes to 0? Or do you mean, say, take fn of x minus f of x, square it, and then say integrate it from 0 to 1 dx? Does that go to 0? When you're talking about functions, not a point-wise convergence is pretty limited, but when you get to convergence of more complicated things like functions, it's convergence in what sense? Or, for example, is it fn of x minus f of x raised to the p power? Does that go to 0? Or more complicated things even than this, with weights. Does the maximum value of this approach 0? So all of these are, the limits imply convergence, but it's convergence in what sense? So we will be exploring a number of different questions in the homework set number 4. I will be giving you probably 10 different limit questions, and you're going to go off and puzzle them through and try to calculate them. And not just give me what they are, but actually more or less rigorously show what the limits are and why they're correct or not correct. Okay, so that'll be the next homework. It'll be a sequence of limit questions. And that should be fun. Let's just tackle the last two questions in the little short amount of time that we have here. And that is, why are limits so difficult to teach, and why are limits so hard for students to understand? Now, you have to understand also that limits historically came pretty late in our mathematical timeline. The Greeks, through Zeno's paradox, had an understanding of a limit. So if I go back to the Greeks, Zeno, either the X or Z, they had the idea of the paradox. How can Achilles here ever catch a tortoise here? Because to overtake him, he first has to travel that amount of distance. But in that amount of distance, the tortoise has gone that distance here. Now, he has to travel here, but the tortoise has gone a little bit further. So how does he ever overtake him? So they understood the idea of a limit, they just did not have the mathematical apparatus to actually compute limits. They thought that you could not add an infinite number of things together and get a finite number. They did not really. They knew it had to be true from physical grounds, right? Because Achilles obviously was faster than this measly turtle, but they did not know why mathematically. So they really just had no mathematical machinery to discuss limits, although they certainly knew there had to be infinite processes. Now, before then, the Babylonians and the Egyptians really, they had some ability type things, but they really didn't have a concept of infinity. It really wasn't up until about the time of Cauchy and Weierstrass, which is, I remind you, is very late. When we're talking 1800s. They actually gave us what we need to discuss limits in a rigorous sense. So we now have a rigorous understanding of limits. Now, the reason why limits are, this should explain that there's something intrinsically hard about the idea of a limit. Why can we go from 250 BC, almost 2,000 years later, why did it take 2,000 years to come up with a rigorous concept of a limit? Well, it wasn't because limits were easy to understand, it was because they were complicated. So what is it that makes the limits so hard? Well, part of it is that limits, you have to deal with limits sort of indirectly. The use of limits and also the understanding of limits is somewhat indirect. Now, what I mean by that is the following. If you understand what a certain, like you know what a function does, you have another function you know what it does, and you say, okay, I'm going to look at what's the limit of this set of functions. Does it behave somehow as n goes to infinity? Well, some of the deepest results of mathematics and some of the most delicate arguments have to do with this. For example, just pulling a limit inside an integral sign takes a great deal of effort and mathematical apparatus to justify. You can't do it for arbitrary functions. They have to be appropriately defined. You can't just take an infinite series of numbers, add them up, and take a limit. There's some very delicate summability arguments. For example, you've all seen conditions on when a series of numbers, Cn, converges. You've seen how many tests are there? Series tests or summation tests. You've got ratio tests. You've got... that's true. Obviously, the series of Cn have to go to 0, but even if the series goes to 0, it does not necessarily imply summability. So you need all these ratio tests, like successive ratios, it goes to 1, or it's bounded above, or comparison tests, and you have ratio tests, comparison tests, you've got Abel summability, you've got all kinds of... Partly because of the Fourier series, people we're really looking at Cesaro summability, all these really delicate ways of detecting whether a series of values would converge. Did it converge at the endpoints? Did it define an analytic function? All kinds of questions about series, particularly when you make these functions of x here. So some of the ideas of the limits are very indirect and require very, very delicate analysis. But the reason why mathematicians use limits, obviously, is that you want to get a result at the end. You have some idea of what's going on, and you have to link a finite process with the end result, and that can only be done through a limit. Let me give you just one last very practical example, and it's related to that Navier-Stokes unsolved problem, and that is if you look at this differential equation, and I apologize for putting down a partial differential equation. This is known as Euler's equation. Now, it has a very interesting concept here that if you were to write, if you look at a line, dx dt, in the x2 plane, equal to u, so a value here, ux0 equals u0, then obviously you can write this as du dt, partial u with respect to t. You can write this as a total derivative, du dt equals 0, right? Because this is partial by the chain rule du dt plus du dx dt. Now, if dx dt is that, then this is equal to 0. But if it's equal to 0 along this line, dx dt equals constant, u equals u0, it's constant along this line. Now, if I have a different slope here, u1, I would have a different slope here, but it's constant on that. But you can see what happens. If u is negative, it goes backwards. If u is positive, it goes forward. And the paradox here is if I start off with a plus value here and a minus value here, and they're everywhere constant, what happens when they intersect? I have a plus value here and a minus value here. What happens at that point? Well, a plus value can't equal a minus value, so there's a shock wave. There's actually a shock that goes off like this. So you have a solution which basically has a jump in it. You have a plus and a minus with a jump. Okay, little quick background there. All of this problem goes away if instead of 0, I add a little tiny number, epsilon, times the second derivative. Now, why should adding a second derivative help? Well, adding the second derivative is a viscosity. And we're really saying, is my problem with no viscosity, no friction, the limit of a series of problems with friction? In other words, if I let my solution be a function of epsilon, satisfying with friction, and my solution with no friction be u, does u sub epsilon go to u as epsilon goes to 0? That's a $64 question. That problem was really only solved very recently in the last 20 years. Okay? But again, it's the limit. We understand how a physical system behaves with a little bit of viscosity. If we cut that viscosity down, yeah, okay, we get more swirling, maybe more eddies and turbulence. But what happens in the limit as you get no viscosity? Well, what happens is you get things which have steeper, this is epsilon positive, you get very steep shocks. So in the limit, as epsilon goes to 0, you have an infinite jump. But even the tiniest little viscosity smooths out these little corners. You see, this is not even really a function, right? It's defined, it has two values at the same point. Okay, and physically that can't happen. In nature, there is a little bit of viscosity, you can't avoid it. And nature, as they say, nature abhors a singularity. Well, shocks are singular, and nature tends to smooth out shocks with this. The mathematicians say, gee, I'd rather solve an equation with one derivative than two. I'll throw it away and solve this problem. Turns out this is much harder than if you kept the second derivative. But again, this is a limit. In what sense is the limit of a series of less and less friction problems equal to a frictionless problem? And that's related to actually that open problem in Navier-Stokes. So getting back to the discussion points, limits are hard in a sense because they're hard, because they're very sophisticated, and because what you're trying to use them for is very sophisticated. You're trying to get at very delicate behavior, maybe in the region of a single point, by solving a very complex mathematical problem. Okay. I will leave that, and probably that will be a question for you, give you a little writing assignment for the fourth homework problem. We'll discuss why are limits hard to teach and why they're hard to understand. Okay, so let's end up. We drew a lot today. And we'll finish with the limits, and the next section will be the next chapter in Boas and Geller.